So next we discuss problem number 11. It says given 1 gram samples of several different gases at standard temperature and pressure or STP, which gas will occupy the largest volume and the smallest volume. So basically you have to calculate the number of moles. Okay. So for 1 gram CO, number of moles of CO is 1 divided by molar mass of CO. So this is 12 is 28. 1 gram H2O, number of moles of H2O is 1 by 18. And 1 gram CH4 is NCH4 1 by 16, and 1 gram NO NO is 1 by 30. Now at STP we know 1 mole at STP, 1 mole occupies 22.4 liter. So here NO has less number of mole number is the lowest here. So this is the lowest mole number. So it gives you the lowest volume, and this is the highest among all 4, highest mole number. So gives you highest volume. So this is the answer for problem B, this is the answer for problem A. So we move to next problem number 12. It says calculate the increase in volume when 500 ml of air is heated from 27 degrees Celsius to 37 degrees Celsius at a constant pressure of 1 bar. So here pressure is constant. So we know PV is nRT when N and T are constant, or N and P are constant, pressure is constant. N and P are constant. We write N and P are constant here. We can write V1 by T1 is V2 by T2. So V1 is given 500 ml. V2 we need to calculate. T1 is 27 degrees Celsius, means 300 K. T2 is 37 degrees Celsius, means 310 K. So V2 is V1 by T1 times T2. So we write 500 times 310 by 300. So we get value of V2 is 516.67 ml. We need to calculate increase in volume, okay, not the final volume. So increase in volume V2 minus V1 is 516.67 minus 500 ml. This gives you 16.67 ml. Problem number 13 says a 5 liter discharge tube containing hydrogen gas is evacuated until the pressure inside reaches 3 times 10 to the minus 5 atmosphere. if the tube is held at 40 degrees Celsius, calculate the number of hydrogen molecules remaining in the tube. So, it is given P is 3 times 10 to the minus 5 atmosphere. Volume is also given 5 liter. Value of R here, since atmosphere liter we are using, value of R we need to use liter atmosphere unit. So, 0.082 liter atmosphere, mole inverse, K inverse, and temperature is 40 degrees Celsius. So, T is 40 degrees Celsius means 313 Kelvin. So, we know PV equals to nRT. So, N is PV by RT, PV by RT. Now, you substitute everything. So, P is 3 times 10 to the minus 5 atmosphere, V is 5 liter, R is 0.082 liter atmosphere, mole inverse, K inverse, and temperature is 313 K. If we do it, we get N is 5.8 times 10 to the minus 6 mole. So, this is the number of moles. So, we have to calculate the number of hydrogen molecules. Okay. So, 1 mole of hydrogen molecules is nothing but Avogadro number. So, 6.023 or 022 times 10 to the 23, and number of moles here is 5.8 times 10 to the minus 6 moles of H2 is 6.022 times 10 to the 23 times 5.8 times 10 to the minus 6. So, it gives 3.4 times 10 to the 18 molecules. This was very easy problem. Now, we move to problem number 14. It says a gas mixture contains 80 gram of dioxygen and 150 gram of neon. If the total pressure of the gas mixture in the cylinder is 20 bar, calculate the partial pressure of dioxygen and neon in the mixture. Okay, so, we start with number of moles of dioxygen. So, number of moles of dioxygen is 80 by 32 is 2.5 moles, and number of moles of neon, or number of moles of neon is 150 gram by 20 is again 7.5 mole. Okay, so total number of moles. So we now consider number of moles of dioxygen. We call it NO2 and N neon. Number of moles of neon is N neon. So total number of moles in the system or in the cylinder, total number of moles, if we call NT, N total is NO2 plus NNE. This gives you 2.5 plus 7.5, so gives you 10. So, partial pressure of dioxygen PO2 is total pressure times mole fraction of O2. So, total pressure is 20 bar and X mole fraction of O2 is NO2, number of moles of O2 by N total. So, 20 bar, number of moles of O2 is 2.5 and total number of moles is 10. So, we get 5 bar. And P neons, similarly we can calculate total pressure by mole fraction of neon. So, mole fraction of neon is, so total pressure is 20 bar and mole fraction of neon is NNE by N total. So, it gives you 20 bar into 7.5 total number of moles of neon by total number of moles. So, you get 15 bar. So, this problem is related to Dalton's law of partial pressures. So, next problem is an unknown gas diffuses 4 times as quickly as oxygen. Calculate the molar mass of the gas. So, first we start like considering let the rate of diffusion of oxygen is R1. Therefore, the rate of diffusion of the unknown gas is 3 times, so 4 times, so 4 R1. Yes, 4 R1. Now, molar mass of O2 is 32 gram. So, from Graham's law of diffusion, we can write rate of oxygen means R1, rate of diffusion of oxygen by 4 R1 is root over of m unknown by m oxygen. So, you get 1 by 4 is m unknown by 32. So, you get m unknown is 1 by 16 times 32, so 2. So, the molar mass of the unknown gas is 2. Next, we discuss problem number 16. It says, given that a nitrogen molecule has a radius of approximately 0.2 nanometer and assuming it is spherical in shape, calculate the volume of a single N2 molecule. Also determine the percentage of space or empty space in 1 mole of nitrogen gas at standard temperature and pressure or STP. So, we know the expression for volume of a sphere is 4 by 3 pi r cube. So, 4 by 3 pi, value of r is nanometers, we need to convert it into meters. So, 0.2 nanometer is 0.2 times 10 to the minus 9 meter. So, we get 0.2 times 10 to the minus 9 meter to the cube. Okay, fine. So, now volume of Avogadro number of volume of 6.022 times 10 to the 23. So, molecules or Avogadro number of molecules of N2 at STP, right? Okay. At STP is 22,400 ml at STP. and volume of one molecule we got from here, volume of one molecule. So, volume of 6.022 times 10 to the 23 molecules is 4 by 3 times pi into 0.2 times 10 to the minus 9 meter cube times 6.022 times 10 to the 23. So, this is the calculated value, Avogadro number of nitrogen molecules. Okay, so percentage wise if we calculate now, so percentage, okay, percentage of empty space. So, this many volume is this is the actual volume and this is the calculated volume. So, percentage of empty space in 1 mole is like, so we have to divide this one by this one. So, we get 4 by 3 pi 0.2 times 10 to the minus 9 meter to the 3 times 6.022 times 10 to the 23, and this is given in ml. Okay, so ml is 22,400 centimeter cube. So, if we convert into decimeter cube, we get meter cube. Okay, so 22,400 times 10 to the minus 6 meter cube. So, 22,400 times 10 to the minus 6. This is in meter cube. So, if we calculate this one, then we get the percentage. Okay, so you need to do the calculation here. Problem number 17 says, if 1 mole of a van der Waals gas at 0 degree Celsius and 50 atmospheric pressure has a compressibility factor Z of 0.7, and assuming the volume of the gas molecule is negligible, determine the value of van der Waals constant. So, compressibility factor, we know the expression is, the expression for compressibility factor is Z is PV by RT. So, value of Z is given 0.7. Okay, so and then pressure is given 50, volume V, and then R is 0.082, and temperature is 0 degree Celsius, means 273. So, if we do it, we get 0.313 liter. The value of V is, okay, so this gives you, if you simplify further, we get the value of V. So, V is 0.7 times 0.082 times 273 by 50. So, this gives us 0.3134 liter. If the volume of gas molecules is negligible, it means van der Waals constant B is negligible. Van der Waals constant B negligible. So, if B is negligible, so van der Waals equation of state becomes P plus n square A by V square times V gives RT, as n is 1. Okay, so we get A is RT V minus P V square. So, value of A is 0.082, RT is 273, V is 0.3134 minus P is 50 times 0.3134 square. So, value of A is 2.104 atmosphere liter to the 3 mole to the minus 2. Problem number 80 says equal masses of hydrogen, oxygen and methane are placed in a container of volume V at 27 degrees Celsius under identical conditions, means at PVT these are all constant. What is the ratio of volumes occupied by hydrogen, oxygen and methane? Okay, so let the mass of the gases be taken to W. So, number of moles, mass of the each gases. So, number of moles of H2O2, H2, if we say this is NH2, is W by 2, NO2, number of moles of oxygen is NO2, is W by 32, and number of moles of and the third gas is methane, so CH4 is NCH4 is W by 16. So, these are the number of moles. Okay, so, according to Avogadro's law, ratio of volumes is equal to the ratio of number of moles under identical condition of temperature. So, here temperature and pressure constant, volumes are different, temperature and pressure. Since number of moles is directly proportional to the volume, so and since W is the same for all, so volume of, so the ratio of volumes of H2 is to O2 is to CH4 is W by 2 is to W by 32 is to W by 16. So, it gives you 16 is to 1 is to 2. This is as V is proportional to N when T and P constants. Okay, since volume is proportional to number of moles when T and P constants, so this is here. Next we move on to problem number 19. If the average speed of gas 1 with molar mass 56 equals the most probable speed of gas 2 with M2 is 44, what is the relationship between the temperature T1 of the gas and temperature T2 of the gas? So, average speed we call C average is root over 8 at T by pi m. So, root over 8 R T1 by pi is 3.14 and the molar mass of gas 1 is given 56. Okay, and then it says that the most probable of gas 2. So, C most probable is root over twice R T by m. So, you get root over twice R T2 by 44 and they are equal. So, C average is CMP. So, if we put the value of C average and CMP, we get root over 8 at T1 by 3.14 times 56 equals to root over 2 at T2 by 44. So, we get 8 R T1 by 3.14 times 56 is twice R T2 by 44. So, we get T1 by T2 is twice R by 44 times 3.14 times 56 by 8R. So this gives you 4, 11. So if we calculate this one, we get T1. Now we can calculate T1 is to T2. Now we can calculate it is 3.14 times 56 by 11. So this is the ratio. No, this is wrong actually. So this is 4. Okay, so this is your 44. So you get, now this is 14, and this gives you 22. This is 7. So it is your so 1:1 basically. So it says that T1 equals to T2. Both temperature T1 and T2 both are equal. And the last problem we discuss here is that the root mean square velocity of 1 mole of a monatomic gas having molar mass m is U RMS. The relationship between the average energy of the gas and the U RMS is. So we know that U RMS is root over 3 RT by m. So average kinetic energy, if we say this is E, is 3 by 2 nRT. For 1 mole of gas, E is 3 by 2 RT. Okay, so if we get this, so if we calculate T here, T is 2 by 3, 2E by 3R. Now if you substitute this T here in U RMS expression, so you get U, therefore U RMS is root over 3 RT by m. So root over 3R times T is twice E by 3R times m. So we get U RMS is twice root over twice U by twice E by m. So this is the value of RMS, and this is the relationship between U RMS and the average energy of the gas.